So, when I was having a conversation with a scientific colleague recently, and I was talking about this process of planetary evolution that um, is of passionate scientific interest to a large community, and talking about how it might be a universal process that we're studying on Earth, might be the development of a kind of planetary being from a barren rock to a potentially intelligent and conscious planet. And he said, "Oh my God, I hope you're not going to include human beings in that." So, this idea that there might be something connected to consciousness that actually has something to do with science and is coming from our understanding of science is anathema to most scientists. But what I'd like to try to do today is to show you a sort of emerging picture of how planets evolve, and that they evolve through a series of events according to laws, and these events are likely to be universal. And if that's true, then the appearance of intelligent life on a planet may be a universal phenomenon, if a planet is lucky enough to make it. So if there are beings from other worlds keeping an eye out on us, and they stop by every million years to take a look. They've come 4,500 times over Earth history. And when they came a million years ago, everything looked good. Planetary systems functioning very well. But nothing to communicate with, no life that they could have an exchange with. And they arrive today, and suddenly they see a planet that just woke up. Just woke up. It now has the capability of understanding the universe, of sensing itself, of communicating with the world at large. And so it would be a great moment when you visit 4,500 times a place, and suddenly you see all this potential. And then you look more closely, and you see what we're doing to the planet. And I think this, this perspective, which is really emerging from an understanding of modern science, is actually very much out of Beelzebub's tales, right? It's sort of what he's talking about, looking at what's happening on the planet Earth. So I'd like to share with you some of the recent scientific discoveries and understanding that show this process of planetary evolution, and address this question, this imponderable question of why we might be here. To put that question not only on a sort of a personal search for consciousness basis, but to place it in the context of a much greater scale, of a large-scale planetary process of which each individual human being may be called to play a part. There she is, our beautiful planet. And we're not alone. When the Hubble telescope was launched, one of the things it did was to take a blank portion of the sky, a small little tiny postage stamp of sky, where it wouldn't be interfered with by stars from the Milky Way, and just open its lens and look. Just wait, looking at the vastness of outer space, which appeared to be empty. And when that emptiness was exposed for long enough, that's what was revealed. Every one of those little splotches is a galaxy of hundreds of billions of stars. And the implication is that anywhere one were to look in the universe, that's what one would see, and one can count the number of galaxies that are in that field of view and extrapolate it to the universe as a whole. And that's where this number of something like 200 to 400 billion galaxies in the universe as a whole comes from. So this is one of them. You can see a second one here. And there's a few hundred billion of those. And each one of them contains a few 100 billion stars, 30 times as many stars as there are people on Earth. So if you go within the galaxies, again, this is an image from the Hubble telescope. We're now going down vastly in scale. And this is an example of something that astronomers call a stellar nursery. So you can see little flicks of light in here. Those are stars. So that gives you the scale of this big star incubator. And this is where stars are born within a galaxy. This is a cloud of dust and gas. There are gravitational instabilities that form within the cloud, and those collapse. As they collapse, they heat up, and if they're big enough, they form a star. And the stars are of different sizes, and they have different levels of energy. So here's a small star. That's like our sun. That's a cross-section through it. It's burning hydrogen in its core and forming helium, and it's running at a temperature of about 60 million degrees. You can get slightly larger stars. Because they're bigger, there's a lot more gravitational compression going on, and they go to much higher temperatures, and they burn up all their hydrogen, and they start to burn helium. And when you get to stars that are about 20 times as big as the sun, then they're so big that their temperature is 50 times hotter, 3 trillion degrees. And they burn up very, very fast. They last only about 1 million years. That's short for a star. And then they explode in a spectacular event, and all the elements that they made in this big process of stellar burning are distributed throughout their local region of the galaxy. So here's a galaxy, and that's an image taken a few years later. This is 59, that's 1972. You see this big spot of light forming here, and that's one of these big stars exploding and sending all its elements out into the universe. And for the brief time that it's exploding, its light is as bright as the light of an entire galaxy. If you take pictures of it later, this is the Crab Nebula, one of these explosions that took place around 1100 AD. The size of the solar system would be something very small in there. So this is the expanding cloud of material from that stellar explosion, where all these elements were made and are distributed into this stellar nursery, and then little stars can form using these elements made by the heroic, short-lived, violently dying big stars, and make long-lived solar systems like our own. So they're big stars and they're small stars. They're a factor of 50 different in temperature. They're 1,000 times different in terms of their lifetimes. They form in the same region of these places, and the big stars provide the elements, and the small stars form long-lived solar systems like our own. All right, so that's a sort of a general statement. How do we actually know there are other solar systems than our own? Because no planet around another star is bright enough to see. How do we know it's there? And actually the first extrasolar planet, they're called, the first planet outside our solar system, was discovered in 1995 only. And about 7 years ago, a telescope called Kepler was launched. And Kepler took a small postage stamp of sky, this time in the Milky Way. And it took its 95 megapixel camera and pointed it at that one thing, and just took picture after picture after picture after picture of that portion of the sky. So here's Kepler's field of view. This is Cygnus, and this is the Kepler field of view just outside of Cygnus, and these are all the little patches that are part of its 95 megapixels. And what it's looking for is this: by taking these pictures of the stars over and over again, it can exactly track the brightness of the star. And it's trying to see if the brightness of the star has a slight fluctuation, very, very small, about 20 parts per million, that would happen when a planet transited in front of the star, a mini eclipse. And so it's looking at all these stars, hundreds of thousands of them, and it's trying to see where there's little dips. And if the dip happens regularly, then they can know that they're looking at the planet going around the star, and in this way they can infer that the star has planets going around it. Sometimes the patterns are quite complicated because there are multiple planets going around the stars. So that's its field of view. It's looking at all those stars, most of them too faint for us to see from Earth. And here are the planets it's discovered in the last 5 or 6 years. So over here we have the size of the planet. That's relative to the Earth. So the Earth is 1 here. This is Earth out here. And this is the orbital period. That is how many days it takes to rotate around its star. So here's Earth. It has a size of 1 itself. And it rotates in 365 days, so it's out here. And these are the blue ones, are the planets that had been discovered before Kepler. And the yellow ones are the ones that were discovered by Kepler. So you look at that and you say, oh my God, there's nothing like Earth in the universe. We seem to be unique. But no, that's not the case. It's just the technology. So Kepler is looking up there, and it's going to find most easily planets that are big and close to their star, so they're causing a big drop in the amount of light that can be seen, and that go around the star very quickly. So it's easy for it to find planets down here which have an orbital period of days. That means just even when they're observing for a month, they can get 3 orbits going around. But if you want to find something like the Earth, it's very small, so it's too small to see in terms of the amount of light that is reduced. And it's only orbiting once every year, so even with 5 years, you only have 5 cycles. Jupiter is up here at this mass, but Jupiter has a time scale way out there, so they can't find anything like our solar system. They're limited by the sorts of planets they can actually observe. But it turns out that when you start doing the statistics on this, that every star has planets. And this is the hottest field in astronomy. So this is showing the number that have been discovered. The first one was discovered back here. And you see this exponential growth in the number of stars that are being discovered. And the green bar here is the amount of stars that are discovered by Kepler. So you can see how Kepler has really been an amazing phenomenon for understanding planetary systems. And they found other solar systems with many planets going around them. So here is our solar system down here, Mercury, Venus, Earth. And here's a system that has the name Kepler 186. And it has all these stars, planets, very close in, rotating around its star. And then it has something called Kepler 1861, which is rotating much closer to its star than the Earth is, but is about the same size as the Earth. And because this star is smaller than the sun, it's receiving about the right amount of radiation so that it would be able to have liquid water on its surface. So the key term here is the habitable zone of a star. So in our solar system, we have the sun. Mercury is very hot, so close. Venus, a little too hot, almost made it, but had a runaway greenhouse because it was a little bit too close to its star. And this green band is the habitable zone of our star, and Earth sits out here in the middle of it. And Mars, if it were on here, would be just outside the habitable zone. Mars is a little too far, so it's too cold. If the star is bigger than this, planets have to be farther away to be the right temperature. But it turns out most stars are smaller than our sun. And so the likely candidates for the first stars in which we might find life elsewhere are those that are fairly close in to their small stars. They're close in so we can find them with Kepler. And the stars are small so that their temperatures are low enough that they can be within the habitable zone of the star. So what have we learned from this exercise by looking at our own galaxy? We've learned that most stars have planets. In fact, there are many more planets than there are stars. We found that Earth-sized planets are very common, and there are billions of Earth-sized planets in the habitable zones of their stars. That's zones where liquid water would be stable. Of course, Kepler hasn't observed billions, but Kepler is looking at this little tiny postage stamp. And then you extrapolate the postage stamp to the entire Milky Way, and that's how you get these big numbers. And the habitable planets we can study are going to be orbiting dim stars smaller than the sun, so not directly associated with our own. So we all thought, well, of course there are lots of solar systems out there, but now we know. And we also know that there are lots of planets the size of the Earth out there, and there are lots of planets within the habitable zones of their stars where liquid water is possible. So it's conceivable that there's billions within our galaxy alone of places where life might have evolved. So solar systems and planets are universal phenomena. And by studying our own planet, we can investigate the possible laws of planetary evolution and consider whether the laws we observe operating here are also likely to be universal. So nobody has any problem with a physicist studying the laws of physics on Earth and coming up with laws, Newton's laws, which are thought to be universal, which apply throughout the entire universe. Or a chemist studies the elements of the periodic table, and we look at the spectra of other stars, and we see the same elements are there. By studying chemistry on Earth, we study chemistry throughout the universe. So by studying planetary evolution on Earth, maybe we're studying a process that is also common throughout the universe. We can investigate whether that's reasonable or not. Well, the stars make the elements according to law, and the most abundant elements are the same throughout the universe. We know that by looking at elements in other stars. And these are the most common ones, with the exception of the noble gases, which are completely non-reactive. Hydrogen, carbon, oxygen, magnesium, silicon, iron, calcium, and sulfur. So Earth is made up of oxygen, magnesium, iron, and silicon, mostly. Life is made up of hydrogen, carbon, and oxygen, mostly. And these elements are secondary in abundance, but still very abundant in the stars. And of course, aluminum is very important in the Earth, and nitrogen, sodium, and phosphorus are very important for life. The universe makes the elements in perfect proportions just to make up planets, oxygen, magnesium, iron, and silicon, and to make up life, hydrogen, carbon, and oxygen. These things are the most abundant elements made in stars, and they're the fundamental character of what interests us on Earth. Well, these elements condense in these stellar nurseries, and they make minerals. And these minerals collect together to form rocks. So this is a primitive meteorite called Allende, which is 4.56 billion years old. It's landed in Mexico 20 or 30 years ago. It's from our earliest solar system, and Earth was made up of these guys. Earth is just a big rock. Well, these rocks have little round things in them called chondrules that shows they formed in outer space. And they also have granules of metal in them. So the sort of dull gray things are rock, and the bright shiny things are metal because this is a polished surface. So when the light shines on it, the metal reflects the light back. So you have this combination of rock and metal, and that's going to be what goes in and forms planets everywhere. And then a process happens of immiscibility, where molten rock and molten metal are immiscible. That means they don't mix together. They're like oil and vinegar. So when you take oil and vinegar and you mix them up, they form a beautifully stratified system with the oil on top and the vinegar on the bottom. And that's just what the Earth did. It formed a beautifully stratified system with rock on the top and metal underneath. This is a very cool oil and vinegar dispenser that I found on Amazon today. You see it has this spout from which you can pour out the vinegar. It's pure vinegar. And it has this spout from which you can pour out the oil. And even though they're in the same container, you can pour them both out from the same thing. How cool is that? you can buy it. So Earth does that. It separates by immiscibility, and this is Earth's core, indicated by the gray, and this is the rocky mantle on the surface. And then on top of the rocky mantle, there's a very thin crust. It's not to scale here. It is to scale on this side of the diagram. It's only 30 kilometers thick, not very thick at all. And on top of that is an ocean, and on top of that is an atmosphere. It's all stratified by density. The metal is denser than the rock is denser than the water is denser than the air, and the crust is lighter than the rocks underneath. So we know this happens all over because we know Mercury, Venus, and Mars have cores. We know that from their density. And when you look at other meteorites, which are broken up, small planetary bodies, they've broken up and you see these beautiful iron meteorites with this gorgeous crystallization pattern. And that can only form from very slow cooling. You can't replicate it in the laboratory. So this is the core of a planetary object that was circling the sun. And this is an intermediate stage where you have a beautiful silicate mineral here coexisting with the metal. They're just in the process of separating. So this process of separating the core, metallic core, from the silicate overlying portions of the planet is you can replicate it in the laboratory. It's going to happen everywhere. And then this metallic core starts convecting and stirring around, and when it does that, it forms a magnetic field. And that magnetic field, here's the Earth, forms a kind of incubation system where the cosmic rays that are coming from space and coming from the star are deflected around the planet. So the planet is protected from this cosmic radiation by this process of planetary differentiation. We know that there were old planetary fields around Venus and around some of the asteroids that were broken up. So this is a universal phenomenon where a planet forms its own self-protection device against the very high energies that are radiating from its star. Now, the rocky interior melts because it's also being stirred around. And as it melts, it sends things up to the crust and into the atmosphere. That's how the ocean forms, that's how the atmosphere forms, that's how the crust forms. This is the eruption of Mount Pinatubo in the early 1990s. And you can see all this stuff. Some of that's rock, some of it's water, some of it's carbon dioxide being ejected from Earth's interior to the surface. This is always going to happen. The interior of a planet is hot, so it melts. When it melts, the planets that life needs, carbon, hydrogen, nitrogen, they're all brought to the surface, water. And so this process of planetary evolution takes all these elements and concentrates them right at the surface, providing a liquid ocean, if it's in the habitable zone, and all the other necessary raw ingredients for forming life. The planet has to be big enough to retain its ocean and atmosphere. The moon went through the same process, but it lost its atmosphere. It lost whatever ocean it had. It's too small, so it can't hold on to its materials. That's why there's so much interest for astronomers in Earth-sized planets within the habitable zone of their star, because the planet has to be big enough to hold on to these magical elements that are needed for life. Well, then another amazing thing happens that when you have continents on the surface and you have an ocean and you have an atmosphere and you have carbon dioxide, you set up a tectonic thermostat that keeps the planet at a constant temperature. So this process of planetary distillation that brings these things to the surface, that creates an ocean, creates an atmosphere, brings up light rocks that float up high enough to be above sea level. This creates, I'm not going to go through this in detail, but this buffering system for keeping the planetary temperature constant. Things are going pretty well, right? So we've got the planets, we've got climate, we've got all the ingredients we need for life at the surface. All of these just simple physical chemical phenomena. So we have our early Earth. It's a layered body by density. It had its metallic core protecting us from solar radiation. It has an ocean, an atmosphere, a stable climate. And these happen by simple physical laws that can be replicated in the laboratory and will be universal. No life. So no oxygen in the atmosphere. So then life begins. One of the great mysteries still, one of the most active fields of all of science at the moment is the origin of life field. All the ingredients are there: carbon, water, nitrogen, potassium, sodium, phosphorus. They're all concentrated at the surface. You've got a stable climate, you've got liquid water, and you've got 1 billion years. So rare things that happen only one time in 1,000,000 can happen when you have 1 billion years to play with. And life is also a magical thing because it takes energy and carries it to its lower state with much greater efficiency than happens without life. So you take a carrot, one of my favorite vegetables, and you take the carrot and you irradiate it so it has no microbes, and you put it in a bag with air. It's out of equilibrium with the air, but it will last for a very long time, will never decay. You leave it out on the counter, and now the microbes have access to it, so it still lasts a few weeks. But if you eat it, it's digested back to carbon dioxide and water in a matter of hours. So we've taken the potential energy of the carrot, and we've reduced it back to its minimum energy state with very great efficiency. And anything that can do that wins. You have something because you extract energy by this process. And so by being in a state where you take these materials and rapidly transform them to their lower energy state, provides energy to the organism that allows it to function and evolve and produce and all those. And this is the fundamental driving force for life. It's actually a thermodynamically favored process. So once life begins, and life begins means just a very simple replicating sac of DNA. And once you have that, then all of the rest of life can evolve from it through the process of evolution and natural selection. So we're all cousins, not just us, but even to the trees and bacteria, we're cousins, because a cousin is somebody with whom you have a common ancestor. And we all go back to exactly the same common ancestor about 3.5 billion years ago. And all of life has evolved from that to the present. And this tree of life, as it's conventionally presented, shows us over here. And you go back in time and ultimately back to the origin of life in the earliest cell. Turns out that most of the genetic diversity of life is made up of these unicellular organisms down here, the bacteria and the archaea. So the first cell would have looked something like this. These cells are called by biologists prokaryotic cells. They're about 0.2 to 1 micron in size. They have just a little strand of DNA in the middle. They have nothing recognizable in their interior. A lot of things happen within their cell wall, and they can divide every 20 minutes. And initially, because the Earth has no oxygen, they're entirely anaerobic. That is, they thrive in the absence of oxygen. So here are some. This is a picture of some of these guys. That's 10 microns. So you can see they're smaller than a micron. Here's another one. That's 500 nanometers, half a micron. So that's about 1 micron in size. These guys are a little bigger, 2 microns. Sometimes they have a little tail that allows them to move around a little bit, or little things sticking out of them. This, of course, would have taken time to evolve. 1 micron, it's 1,000th of a millimeter. So if you take a little bit of your skin or something, and you imagine 1 millimeter, it's an incredibly small thing. But there could be 1,000 microbes if they were packed end to end, 1,000 by 1,000. So there'd be 1,000,000 of them on 1 square millimeter of your skin. Makes washing your hands seem important. And they have evolved to occupy all the different interstices of our bodies. They live in our hair follicles, they eat our dead cells, they're continually processing our skin, they live in our gut, they live in our intestines. Trillion of them, all our microbiome operating on our interstices. And they're incredibly diverse organisms and incredibly flexible. And they're everywhere. Every surface that we see here is covered by these microorganisms. They're so small that even when you put them in a microscope, you just see these little dots. It's very hard to know what they are. It's very hard to know what they do. There are probably 1 trillion different species of them, but you can't tell what they do by looking at them. You just have to look at their DNA. And so this is another view of the tree of life. And we're over here at the end of one of these little loops. All of animal life, all of metazoa is over here. And this is the genetic diversity of the bacteria. There are 1 trillion different species. They can do anything. They can process oil. They can go and take a stick of sulfur and oxidize it and live off it. Wherever there's energy potential, they evolve to take advantage of it. They're absolutely amazing creatures. So this is a 2 foot by 4 foot petri dish. And it's going to have E. coli put on the 2 ends of it. And then there's going to be a band here where they put enough antibiotic to kill the E. coli. E. coli is one of these kinds of bacteria. And we're going to see how the bacteria evolve in dealing with difficulties in their environment. So these different bands, this has just enough antibiotic to kill the E. coli. That has 10 times much, 100 times as much, and 1,000 times as much. So that's 1,000 times as much antibiotic that is needed to kill these guys. And this out here has no antibiotic. It's just an agar, so they can grow happily on it. And so these numbers appearing on the screen, this is done by colleagues at Harvard Medical School. And so they're going to inoculate a little bit of E. coli on these 2 ends, and the bacteria have lots of food, so they multiply. They have a reproducing time of an hour, so you can make 1 billion of them in 24 hours. So they can propagate very rapidly. That's how we can get sick so fast. Now you're dropping the E. coli in at the 2 ends. It reaches the first boundary and it can't go further because the antibiotic kills it. And then a mutant appears. And the mutant has adopted resistance to the antibiotic. And so it starts propagating. Other mutants appear, and they're all competing with each other now, because they would have had different mutations that give them the resistance. And as it keeps on going, it reaches the next boundary, where there's 10 times as much antibiotic. It slows it down a little bit, but it keeps going. Now it's going to reach the 100 barrier until another mutation appears, and it's able to go towards the center. Now it's reached 1,000 times the concentration of the antibiotic. This has taken 11 days. It's a very short period of time, and it moves forward and slowly occupies the entire petri dish. Incredibly flexible organisms, right? They are so capable, and all of these show the mutations. This is mutation and natural selection happening in real time. This is a very different organism than the one that started with. It's happened in only 11 days, but or 12 days. 12 days, that's like 400 generations, okay? So that gives it a lot of potential. 400 generations for us is like 12,000 years, and these are very simple organisms. So this is the way that life was on the early planet, and you can see how flexible and creative it could be. So these early organisms lived on an oxygen-free world, and they needed to make a living, and they did it making use of hydrogen and sulfur, which were very in low abundance in the environment. So there were limited resources for them. And there was no agar for them to grow on. Agar would be made by human beings to help them. And without using oxygen, when they metabolized their food, they got 2 energy units per molecule of sugar. So life in this time period was resource limited and energy poor, but still very creative and evolved to fill every ecological niche. So then life made an amazing discovery, which was photosynthesis. Now, photosynthesis makes use of carbon dioxide and water. These are everywhere. And so they're no longer resource limited by these fundamental molecules. Instead, resource limited by things like nitrogen and potassium and phosphorus. That's why we use fertilizer. So photosynthesis takes carbon dioxide and water. It makes sugar, that's this, and it creates oxygen as a waste molecule. And this allowed life to harvest sunlight and make use of abundant ingredients. So these photosynthetic organisms take over the world. They adopt all the top of the oceans. They become the most abundant organism on Earth. But they have one big problem, and that is that the oxygen that they formed here was a toxic pollutant, because oxygen destroys organic molecules. So they were making their own poison. This limited the spread of life at that time. And so life started back here around 4 billion years ago. Then photosynthesis evolved. And when photosynthesis evolved, the oxygen level went up. This is oxygen on the vertical axis over here. But then you reached a threshold where you couldn't raise oxygen any further, because if you did, you were killing everything off. But this is a long period of time, 1 billion years, where these organisms can develop resistance to oxygen just the way the E. coli developed resistance to antibiotics. This required a long period of time for them to do this. And furthermore, when they made the oxygen, even when they could tolerate a little bit better, the entire surface of the Earth contained elements that gobbled up any oxygen that was made. So dark black rocks have reduced iron in them. The rocks turn red. That consumes the oxygen. Earth's surface had to become rusted by the oxygen that was being produced by the photosynthetic organisms. And then the very clever microbes discovered a new thing. They discovered that if they were to use oxygen to burn the glucose molecules, they could get 36 of these energy units. Not 2, but 36, a factor of 18. That's like an animal that can only move at 10 miles per hour, suddenly being able to move at 180 miles per hour on exactly the same food intake. It's an incredible biological advantage. So I call that an energy revolution. And the organisms that were able to do this gradually began to take over the world, and it allowed also a complete change in the character of life. So some of the prokaryotes carried out photosynthesis to make their own food. They produced oxygen as a waste product. Others evolved the ability to process the oxygen, but they need food. So they eat the early plants. They're not really plants, they're just photosynthetic organisms, and also get rid of the oxygen by the way we get rid of oxygen, by breathing and consuming our food. The organisms that can do this get 18 times as much energy per molecule. It's a big energy advantage. And by combining forces, they can make a new kind of biological machine, the eukaryotic cell. It's still a single-celled organism. And when it's looked at closely, this is its membrane, and you can see it has all these infoldings. And some of these little things called organelles have their own DNA. This is actually just a big partnership. They combined the capabilities of all these little prokaryotic organisms into a single bigger organism, and then these guys could no longer survive outside this organism, and this organism completely depended on the partnerships of these little guys that they included. And so you made a completely different scale of life. So this happens around 1.7 billion years ago. They're about 10 times the radius, so 1,000 times the volume. They have a cell nucleus. They have 1,000 times more DNA. They take 24 hours to divide instead of 1 hour. And they're normally making use of oxygen. We call that aerobic. This is a whole different dimension of life. The prokaryotes still exist in overwhelming abundance, but these guys tend to dominate the ecosystems. The same world is there underneath them, the prokaryotic world, and then a new world is built on top of it of a different dimensionality. So here's the two types of cells. A simple little prokaryotic cell, little tiny guy, 1 micron in size. And the giant eukaryotic cell, still a unicellular organism, still too small for us to see with the unaided eye. So the individual organisms for most of Earth's history were completely invisible. You could see communities of them because they'd make a sort of bacterial slime. The bacteria are these little shimmering things over here, very, very small. You can't see them. There they are. You see, they're almost invisible. Now, here are eukaryotic cells. These are paramecium. And they're much bigger. This is all at the same scale, so you can see how big they are compared to the prokaryotes. And they're very flexible. They can move around. They're eating these little prokaryotic cells. They communicate with each other by touching. This is two of them undergoing fission. So they're reproducing by separating and forming two. Paramecia can do that up to 3 times a day. But they can also reproduce sexually. And so here's 2 Paramecia that are exchanging genetic material. They look very happy. When they do that, they live longer. So there they are. You can see another eukaryotic organism that's made a whole chain of cells here, forming a kind of initial eukaryotic community. That's the eye of a needle. And now you can see the paramecium swimming around in the size of the eye of a needle. That's the scale of this world, a whole universe in the eye of a needle. This is another eukaryotic organism called the swan. It has this beautiful neck that it goes out and it grabs up prokaryotes and eats them. Imagine if your arms could do that. This guy he has a little rotor on his mouth. And so he sends up the rotor and he sucks in the prokaryotic cells, just like a little vacuum cleaner. You see, the eukaryotes are very, and this guy's a real monster. So he goes around and eats the poor paramecium. You'll see him do that in a second. Pop, lunch. So he ingests it, he'll eat it. And here's another guy with his spinning vortices on his mouth, pulling in the prokaryotes to eat them. You can see them. He's so greedy. A whole universe on the scale of the eye of a needle. These are prokaryotes that are forming little communities. So those are prokaryotic cells, and this is something called Volvox. That's 50,000 of these prokaryotic cells forming a round spherical community. And of course, that gives them great protection against the eukaryotic monsters. 50,000 guys, and it actually reproduces a whole. Here's a community of eukaryotic cells that is working together. They can do amazing things. This is another community where they're forming groups end on end, something called spirogyia. All of these are the individual cells that are manufacturing these long filaments. You can see the little prokaryotes swimming around. At some point, these eukaryotic cells, they love oxygen. And so they actually benefit from higher levels of oxygen. And they have the protection against the oxygen poison, so they're able to live for a long time in the presence of oxygen. And this allows oxygen to build up in the atmosphere. It starts happening around 1.7 billion years ago and ends around 650 million years ago. And once it reaches this level, it provides ozone protection. And once you have ozone protection, then life can emerge out of the oceans and go onto the land. So oxygen is originally a poison. It gradually oxidizes and modifies the planet. It changes the compositions of the rocks in the ocean. Life adapts to it. And when there's high enough oxygen to provide ozone protection, and it allows things to go onto the land, and then you can breathe. So you don't just have to absorb the oxygen from the water. You can actually breathe it in like we do, and that provides a still higher level of energy available. and another transformation of life. So the eukaryotic cells form partnerships like the prokaryotic cells did. And the number of cell types through time gradually has increased. So we have about 275 different cell types in our bodies, but the first multicellular organisms only had a few. And when they became a little more complicated, they became this sort of size thing, about an inch in size. This kind of life that we could see didn't exist for 88% of Earth history. And so we can see this progressive change from the first primitive cells to the eukaryotes, to the eukaryotes first appearing by relationships and partnerships. And then you get the first multicellular organisms in the oceans, and then you breathe the air and invade the land, and then you get mammals, and recently you get us. So life appears to be a natural planetary process. And I hope you get the sense of how this relationship business is very advantageous. When these organisms form relationships with one another, they acquire an evolutionary advantage. And the discovery of photosynthesis is very advantageous. And you have 1 billion years to do it. So you have plenty of time to try to make it happen. And then you develop the oxygen protection, and you can get more energy from the oxygen. So that's a very natural thing for the organisms to do, because they're always competing with one another. And the scale and dimensionality of life is then increasing through time, from little tiny things that we look at them and we have no idea what they do, to the eukaryotic ecosystems that are familiar to us, even though we can only see them under a microscope. But we see people having sex and eating and talking to one another in their own way. And all of this is happening in these periods of homeostasis, followed by change to a next level, a new dimension. So this evolutionary process of the planet is proceeding by increasing access to energy and increasing ability to relate. So you can see where we're going and asking how humans fit in. Well, it turns out there's an advantage to being smart. So here are grazing animals and carnivores, and this is different times. That's ancient times moving up towards the recent. And the carnivores are a little bit smarter than the grazing animals, which they have to be in order to catch them. And because of that, as the grazing animals get smarter, they can compete better. And that means that the carnivores have to get smarter. And so everybody gets smarter together, with the carnivores staying a little bit smarter than the grazing animals. But the brain size here is up by about a factor of 7 compared to what it was just a few tens of millions of years before. So you can look at the evolution of the apes, and there is also the evolution of brain size. It's not just the size of the brain, because Neanderthals had a bigger brain than we do. Something about the way the brain is organized. And when you look at a human being, it is now a partnership of 1 trillion eukaryotic cells. All the cells that we can see and that we talk about are kidney cells, liver cells, brain cells, nerve cells, blood cells. All those are eukaryotic cells, the big guys. And they've formed now a partnership of 1 trillion or so. And that's what makes up each one of us. And we have 10 times more prokaryotic cells living on us and in us. That's our microbiome. And so imagine the infinite possibilities of sensing and relationship from this vast multicellular machine. So the first modern humans appeared about 200,000 years ago. They had fire because hominins before Homo sapiens had fire more than 1 million years ago. They developed language. We don't know when that happened. 190,000 years passes, and then about 10,000 years ago, you get the first civilizations and the development of agriculture. The civilizations rose and fell, often from using up resources, wars, and natural disasters. The Assyrians and by the Tigris and Euphrates were incredibly successful civilization for hundreds or more than 1,000 years. And by tracking the grains that they were growing, they can tell that they gradually were irrigating their fields with more and more saline water, because they had to get the water from the mountains in the north. And so the water flowed down in the snowmelt, and then they stored it. And when they stored it, it evaporated and became more saline. When they did this over centuries and centuries, they deteriorated their soils, everything became saltier, and so they had to change from wheat to barley. They become vulnerable. Soil degrades at a slow rate, even though they were very careful. So the very rich soils that were there gradually thinned and thinned. They had concentrations of people, and then in a very short period of time, they disappeared. The Egyptians went through various dynasties. The Greeks, of course, disappeared. The Romans disappeared spectacularly. It wasn't just the sack of Rome. It was a progressive deterioration over about 100 years, often having to do with food, with the erosion of soils, with deforestation, which was the source of their fuel, then plague, famine, and war. Rome had 1 million people at the height of the Roman Empire. A couple hundred years later, it had 60,000. The Maya, the Inca. Cities that were in existence for hundreds of years, far longer than San Francisco, New York, and Chicago. In 1500 BC, they disappeared in less than a century. They disappeared in such a short period of time that archaeologists can't tell how it happened, how quickly it happened. Just bam, destruction. The Crete civilization probably was destroyed by the eruption of Santorini in the Mediterranean. We haven't had a big volcanic eruption in all of modern human history. So we see that civilizations come and civilizations go, and they go from these kinds of processes, using up resources, wars, and the natural disasters, which we have not really experienced, but climate change might be one. So the most recent civilization is our own. It's a few hundred years old. These guys generally lasted 400 or 500 years. Now, in the process of our most recent civilization, there's been a change which is entirely different from all the previous ones, previous civilizations. And that has been the discovery of fossil fuels and the ability to extract energy from them. So, although you can get a little bit of energy from fire, most of the energy for people throughout human history came from eating. And when you eat, you get 100 watts of energy. That's down here, this line. This is watts. So each of us is a 100-watt light bulb from eating our food. Global average energy consumption is 2,300 watts. Europe is in here at around 5,000. USA and Canada up more than 10,000. So that's 50 to 100 times more energy per person than is available from food. So that's an energy revolution that is unprecedented in all of Earth history. The oxygen revolution produced a change of a factor of 18. We've now produced a change of a factor of 100. And that's what makes us supermen, able to fly through the air, look through walls, kill people thousands at a time. All these things are possible because of this access to energy. This is the biggest energy revolution in Earth history, and it's happened just in the last 100 years or so. And then there's this change in relationship that human beings provide because we can talk to each other. Language is an incredible way for us to communicate and establish relationships with one another. And then there was development of books and printing, which allowed communication over distances where people were not in personal contact. We've developed mass communication early in this century, and then the internet, which allows all of us, except for this brief time interval when our phones are turned off, to communicate with people all over the world instantaneously. And we've developed systems of planetary sensing, where we have measurement of planetary properties everywhere. We know all the earthquakes that are happening. We know the temperature everywhere. Here's earthquakes and how they're distributed around the world. We have a network of seismic instruments that's listening to the earthquakes all over the world. The earthquakes are sending waves through Earth's interior, and those waves are telling us all about the interior of the Earth. So we have interior sensing of the planetary body. And we have satellites that are circling around the Earth and providing. Elon Musk now wants to put a series of satellites at regular spacing all over the world, so everybody's in communication with everybody all the time. It's kind of constant sensing. If you were to look at a map of the world, and I've been wanting to do this but haven't done it yet, and you start in the 19th century with the laying of the first cable, which happened in England, and it was about 2 kilometers long. And then if you just looked at the growth of cables all over the planetary surface, it would be like the development of a planetary nervous system. So now you have trillions of miles of cables all over the planet where messages and communications are moving backwards and forwards. So we have this process, this planetary evolution process, where we have this initial state where the planet just reflects the solar energy that comes to it. And then gradually, life is able to use that energy through photosynthesis, for example. It's absorbing it. It's using in more and more of the energy from the sun to create planetary systems. And in the early Earth, you couldn't breathe, you couldn't light a match. And now we have a modern Earth where energy is available everywhere. Uniquely in the solar system, we can light a match, we can breathe, we can light a candle, we can run a car. All that is because of this developing capacity of the Earth for energy. And life evolves along with this from a lifeless surface like the moon. And you get the microbes that populate and transform the planet, and eukaryotes appear. And then you get complex ecosystems like we have today, populated by organisms like ourselves, made up of trillions of cells. So life is entirely planetary. Planetary process. We are all planetary beings. We are intimately related to this 4.5 billion years of planetary evolution. We can't go live on Mars. Can't go live on the moon. We are tied in every fiber of our being to the way that the Earth operates. And life evolves with the planet and gradually transforms it. In this process that we see by going through Earth's story today, we see there vast periods of time of little change, punctuated by a kind of planetary molting to a new level of function. And each one of these moltings involves access to increased energy and increased scale and dimensionality of relationship. So here we are, we're 1 trillion eukaryotic cells forming a single organism. We host another 1 trillion of the prokaryotic cells. We coexist with ecosystems of eukaryotic cells like exist in a drop of pond water. So the same world is there that was there in the early Earth, prokaryotic world, and it's been gradually increasing levels, increasing dimensionality, increasing size, increasing function. So what's the role of human beings in this process then? In an ordinary way, you could think of a human being as a particle, a cell of a planetary brain. We have the ability to understand the planet as a whole. We have the ability to act for the benefit of the planet. We can bring the capacity for communication with other planets in the universe. We bring planetary awareness. We bring these functions that we would ascribe to this word consciousness in the ordinary sense. Where do I come from? How did I get here? How do I fit into something larger than myself? Am I here? Am I aware of my surroundings? Those questions that we can ask ourselves are now questions that through us, the Earth can ask itself. So, am I that kind of human being? No. And what would it take to become one? Because I think to be such a human being, it would mean to live related, to live related to the world. And of course, a selfish life, a life driven by dreams, is not such a human. So in this way, that it appears that the appearance of human beings is not just some planetary accident. It's the outcome of a planetary process, perhaps a universal process, because all the different steps make a lot of sense. And here we are destroying a long-standing homeostasis of the Earth system. We're in the process of this molting event. And there's the potential for us to be the terminal point of planetary evolution. We die off. The microbes are still there, but the planet no longer can evolve. And so this might actually become not just a fun idea, but a deeply personal question. Could I be a cell of planetary consciousness? Or am I really just a kind of cell of planetary cancer, using the planet for my own personal and egotistical aims? Now there's another important lesson, I think, from looking at the evolution of the Earth, which is everything took time. When we looked at these different processes, we were talking about billions of years. And here we are in the process of what's happening now, and it's been 100 years. So maybe it's a much longer term process than we realize. Maybe it's necessary, like with oxygen, it was initially a poison and killed things off. Maybe human beings are kind of initially a poison and have to kill things off. And so the human beings then have to learn and evolve and die back and then grow back and gradually develop this relationship with the planet that would allow the planet to undergo through this process. So for this reason, I'm not it gives a different perspective on the environmental crisis, which of course is hugely moving for us whenever we're sensitive to it, which is not very often. But maybe that's just one step in a much longer game that we're not aware of. And so there's something about developing slowly this potential to be a different kind of human being, and having that happen over long periods of time might be necessary for the planetary system. So this question of Earth and human is, it seems to me, the central question of our time. The relationship of us to the planet on which we are entirely dependent and to which we owe our whole lives. Thank you.
Charlie, that was extraordinary. And now maybe there are some questions.
Can we turn up the lights and turn off that?
Turn up the lights, yeah.
Thank you very much for that. One question or one issue which you did not address was, how did DNA originate in the first place? Now, you will be, of course, very well aware that Crick and Watson discovered DNA. And one of those two gentlemen said, around about the time or shortly afterwards, that to create DNA was like, for example, putting an ape into an aircraft junkyard and asking it to build a jumbo jet. such was the complexity of that particular element of life. I wondered if you had an explanation for that.
They're geniuses, but not geologists. So the critical thing that's missing is billions of years. So when you take something like the formation of DNA or the development of the eye, it seems incomprehensible that the changes could happen. But the example that I like to use for this is language. So language is something that is, steadfastly transmitted from parent to child. So the child learns the language from the parent and picks it up exactly. And if you listen to a Shakespeare play, that's only 10 generations ago, and the language of Shakespeare is very different. And if you then go back and look at Chaucer, you see let's see, there's Beowulf. Who wrote Beowulf? Oh, come on, you guys are Brits. Anonymous. Oh. All right, there was Chaucer. When was Chaucer? About 1,000? Slightly later. You go back to Chaucer, and it's beautiful to listen to, and you can barely understand a few words. And when you go back to Old English, a few hundred years before that, the language is completely unrecognizable. So that's through something that was steadfastly transmitted from parent to child with great dedication. In only 1,000 years, that's 30 generations. So this process of slow change can lead to very large changes given enough time. And so when we look at something like DNA, the biologists now think that DNA evolved later, that RNA evolved first, which is much simpler to do. And then once you had what they call an RNA world, then somebody gradually developed the possibility of DNA. DNA has the advantage over RNA that it's a much more durable molecule. And so it could evolve like that over hundreds of millions or a billion years in early Earth history.
Would you say evolution is a process that has some sort of conscious being presiding over it?
No. All the processes that I described are physical chemical laws. They don't require any intervention. So it could be that there's an intelligence that provides the laws. So if the intelligence sets up the laws, then the universe unfolds in a certain way. But it's not someone who's looking at it and saying, I think blonde hair would be nice, and changing it. So when I speak to some of my students, since I teach in America, a fair number of students are evangelical Christians. And they ask me, the kinds of questions that they were taught by their ministers and parents. And I suggest that it's actually a kind of an insult to God's intelligence, that he's got, 200 billion galaxies to deal with. So given that, is he going to have to go in and say, okay, no, we need to make eyes on planet Earth? Evolution is so elegant. It allows the evolution of complex life with no action on his part. It's a divine intelligence compared to direct intervention.
Okay. You talk about evolution ongoing, but does it come to an end in the same way that a tree goes to a certain height and then stops?
Yes. Yes, the sun will die, the earth will die. But not for a few billion years, so we're still on the hook.
But the human experiment will come to an end before that, surely?
We don't know that.
Mm.
So the critical question for life in the universe is the lifespan of intelligent life on a planet. So if a planet develops intelligent life and civilization and then self-destructs after 10,000 years, then you have 4.5 billion years of planetary history, and it just pops up and disappears. So in that case, consciousness in the universe would only be like just a flicker, little points of light popping off every once in a while in the galaxy. Maybe there's only one present at any one time because the lifetime is so short. So if it's a conscious universe, then these civilizations have to last for a very long time. And if they last for millions or tens of millions of years, then they have developed and evolved in ways that it's impossible for us to imagine. So all the restrictions we know on interstellar communication and so on, all these things that we always think we know everything, but we're universal cavemen from that perspective.
You didn't explicitly say this, but I assume that your view is that life has evolved or is capable of evolving all around the universe. And my second question is, do you think there's any realistic possibility of communication with any other forms of life on other stars or solar systems?
Yes, it's terrible if I didn't state it explicitly. The central theme of what I was trying to say is that planetary evolution giving rise to intelligent civilizations is likely a universal process. That's the message that I was trying to convey. Okay, sorry, I forgot the second part of your question, which was more interesting. Remind me. Yes. As we sit here and look at the evidence for the Big Bang, for example, we get that from observing the galaxy around us. And every other intelligent civilization will come to exactly the same conclusion by making those observations. So when we ponder and think of the Big Bang, there could be a being on a distant galaxy millions of light years away at the same moment looking at that truth of the universe and sharing that experience with us, sharing the experience of presence to the grandeur of the universe. Now, this is one form of communication, of shared experience of the universe itself. Now, as far as the question, are little green men going to come down and see us somewhere? Life is incredibly planet specific. And it's not only planet specific in terms of the planet, it's planet specific in terms of what time on the planet. So take us back 30 million years ago, there's nothing for us to eat. When human beings from Europe came to America, after they'd been separated by only a few tens of thousands of years, the diseases wiped out most of the American population. So when I travel to India, I get sick. Why? Because life is so specific. Specific to food in Boston. I go anywhere else, my digestive system gets messed up. So imagine the problem then for a being from another planet trying to actually visit us. They can't. Their whole 4.5 billion year evolutionary trajectory will be completely different. There's no world, no universe like Star Trek or Star Wars or something where you pop into a bar on a planet or in some distant galaxy. It just can't happen. So the only way then for communication would be the way that Mr. Gurdjieff actually suggests, that a being through knowledge of biotechnology is born on a planet with the knowledge, the ability, the right appearance, the right biology, the right language. If that kind of individual could appear on a planet, that would then be the way that to communicate with the beings of that planet. It wouldn't be by sending down some strange creature that would scare the living daylights out of us and either kill us or die just because of the biological incongruity. So I think his idea is, I don't know if it's an idea. I think what he says is a very sensible way for communication with other intelligent civilizations to happen.
I just wondered what you did at the bottom of the sea.
Oh. Well, I was, last week I was trying to get my diving certificate in Ustica, and that's why I have this cold. So that was 10 meters. So to go to the bottom of the sea, you have to be in a submersible that is able to protect you from the pressures because you're 4,000 meters down. It's a 2-meter sphere. You're there with 2 other people, one of whom is the pilot, and you're looking at a little porthole, and you have all kinds of instruments that are trying to tell you. As you go down, you listen to Bach or Mozart, and you look out your porthole, and you see all of the luminescent life in the ocean. So it's like traveling through space. And then you get down to the bottom, and the submarine comes to life, and the motors start whirring, and the lights go on, and you're there. And it's a little bit like this, you know. I'm looking out my window. Nope. Nothing. No, I don't see anything. Nothing's happening. All alone. And the person on the other side is like, holy cow, look at all those people out there. There's a whole audience. And you kind of, wait. So it's very exciting, but also a little frustrating.
I'd like to know what's the relationship between well, life and intelligence and consciousness. Because I mean, there's this evolution, you know, which you've described so well, of intelligence, but you know, and there's artificial intelligence. But what about consciousness?
Well, I think it's clear that there's a different dimensionality to the human being than there is to any other animal. So the human being is bringing a different dimension, not only in terms of relationship, like being on our cell phones, and energy, being in our cars, but brings the possibility of a different quality of relationship with the universe, which is potentially transformative for a planet. But and that's a subject of great interest to everyone here.
It's another step. Sorry, perhaps that's too crude a way of putting it. I mean, consciousness.
Hi, yeah, I wanted to ask about the role of artificial intelligence specifically in the evolution of the human. For example, do you think that we're looking at the end of the organic human as we know it? Thanks.
I hope not. The artificial intelligence can do certain things very well. It can play the game of Go very well. It can play the game of chess very well. And it can process large amounts of data and find patterns and can develop fast algorithms for doing things like facial recognition. So it has huge technological capability. But I don't see how it can ever have this special sensitivity that a human body has. Could be wrong. There's you know, we talk about all the wonderful instruments that science is able to develop, but there's no instrument like the human body. We're sensitive at the same time to sights and sounds and smells and temperatures and inner experiences and outer energies. And so there's this, and capacities that are unknown to us, that are touched maybe only briefly during special experiences, showing sensitivities of the human organism that is of a completely different dimension and scale. So no computer based on zeros and ones can have that capacity, in my view. When we're hiring new people at Harvard, a lot of the new people come in and they want to say they're doing, you know, the best stuff with artificial intelligence and so on. And it turns out that to use artificial intelligence intelligently is very difficult. So if you have a really well-formulated problem, like facial recognition or playing chess or something, artificial intelligence can do much better than an individual human mind. But for the real complex world in which we live in, artificial intelligence is pretty helpless so far.
I was fascinated with the very early forms of life, how it seemed that the form of whatever was not separate from the environment. It was like it was part of the environment. But at the same time, it was so striking that each one had, it was this word transformation that struck me most, that it had something else, which was, it was transforming something. And the fact that oxygen existed, but it was poisonous, and yet creatures evolved, if you like, or were present suddenly to be able to transform that oxygen by respiration. I think that's extraordinary, the beginning of breathing. And it seems like, I wonder if that's a clue, this transformation of something into something else, especially something like, you called it a poison, into something that would take, you know, something to another stage. I think that's extraordinary, if I understood it properly.
Yes, and technology could be a little bit like that. Right now, technology is a little bit like a poison. We're poisoning the planet with it.
Well, just saying that we carry on the way we're carrying on, and we end up killing our form of organic life, then am I not right that there are the entire bacterial models, in fact you had them in one of your diagrams, that exist using thermal energy? And given these billions of years, might not a completely different form of complex life evolve from those?
Maybe. But you know, I didn't talk about fossil fuels, but our transformation to a technological society has come about because of the availability of fossil fuels. It's like fossil fuels are this stored energy currency in the earth, built up over 400 million years. And then we come along, and it doesn't matter if it's a century or a couple of centuries, we use up 400 million years of this planetary treasure in a couple centuries. Just now we all say, oh my God, that's terrible. It's terrible. But maybe that's part of this process, because you have to have access to some form of energy to develop the capabilities that we have of planetary sensing and planetary communication. So the energy is stored up in the planet, and then intelligent life comes along and there it is, makes use of that energy, and then it develops the technology for wind power and solar power and fusion and so on. And so then that energy is no longer needed, because the technology is developed to have access to energy that doesn't depend on it. It's sort of like a primer, like a starter. You know, when you're starting your car, the old days you had to crank it up. Maybe the fossil fuels are a bit like that. So the thing is, once you use them up, then they're not there anymore. So you don't get the chance to start again for another 500 million years.
Geothermal energy, I mean.
Well, geothermal
loads of it.
energy is also requires quite high technologies to extract.
I have to say that you made me very uneasy. I'm not sure I'm going to be able to actually say why, but I was a little bit reassured when you said that maybe God made the laws a bit earlier. Initially, you were sort of painting a universe that more or less existed for itself. As I say, I'm not sure I'm going to be able to really say what my question is. But you can't be saying just that. I've come to the conclusion. So what are you really saying? Do you know what I mean? Am I making any sense?
Well, maybe the universe exists for consciousness.
So in that case, consciousness must be outside the universe.
No, within. I mean, okay. What I've tried to do is to separate what I'm saying from these more esoteric questions. Okay?
Yeah, now I gather that.
And a lot of your questions are about this esoteric stuff, and I'm an expert in certain subjects, some of which I've talked about here today, some of I'm not, but in terms of those subjects, I'm not an expert. So what I've tried to do is say, look, it's a little bit like when I was in my 20s, I went to my godmother's over Christmas vacation, and it was raining and cold, and so she brought out this huge box that had all these jigsaw puzzle pieces in it, beautifully cut jigsaw puzzles with you know, made of very special plywood. And she dumped it on the table and she said, here, this will keep you busy. And so we started putting together the jigsaw puzzle. And you know, with a jigsaw puzzle, you try to set up the sides so that they're straight and everything. There were no straight sides. It was a completely weird shape. And so you had to sort colors, and there weren't that many colors. And we worked at it, and gradually, we put the puzzle together. And then we said, oh, it's a Santa Claus. It was a big, beautiful Santa Claus made of about 3,000 pieces. And that to me is a little bit like what's happening with earth science right now. We have this huge puzzle. We don't know what it is. We're starting to look at it. And then we're saying, oh my God, look, there's this process of planetary evolution. And we can't think about putting human beings into that process, but maybe intelligent life has a place. Maybe we're looking at a process of how a planet evolves from barren rock to conscious being, in which case intelligent life has a role to play in that evolutionary process which we are studying. And how amazing is that? And so that divorces it from esotericism. Like, it just says, here's this process, and it looks like maybe human beings have a function. And yet we're not able to fulfill that function. We don't live that way. So what would have to happen within us that we would be able to live that way? And so that then informs a search for what would it be to be a conscious being, that is, to be a part of this planetary process that we can't understand, but we're just beginning to see, like the emergence of the Santa Claus puzzle.
Charlie, you've been incredibly generous with your time, and I think your voice is possibly beginning to feel the strain. Thank you very, very much. It's been very interesting.